Alright nerds, so right now we're going to look at something called sound waves. So we want to understand what sound waves are and how they travel, and what we're going to be able to look like. When we can understand that, we should be able to draw a representation of a sound wave as a compression wave and label it like rarefaction, compression, that sort of stuff. So what is sound? Basically, it's the periodic disturbance. So in a cycle, and then moves backwards and forwards, of an elastic medium, which means it's going to return to its original position. So there's probably two new words, or two possible new words, such as air. In other words, when the air is disturbed, it moves this way, then that way, and then rests back to its original position. But it might do that more than once, or it will do that more than once, and eventually it'll come back to its original position. And we see that here, right? So here we have air which is undisturbed, and then we imagine there's a speaker at this end, pumping out sound. It's like Slayer or something. That's rad. So red blood. And then we see the waves here are compressed because the air particles have all come nice and tight, and here they are separated away from each other. It's not dense at all. So what this means is air particles, so we'll say they're roughly here, would be this one's average position, and it's going here and then back to here. So that's your wavelength right there. Sound waves will travel through a vacuum. Won't travel through a vacuum. They need a medium. Because they travel via oscillating particles. Some energy will be able to travel via the energy is the particle itself, and that's for light. But sound is not one of those. It needs a medium, so it won't travel through a vacuum. They're compression or longitudinal waves. They're not transverse waves. We can draw them as though they're transverse waves here to compare it. And often, to be honest, when you see a sound wave drawn, it will usually be drawn like this. Ignore the dashed line. That's a different thing altogether. The solid line is the one we're focusing on here. And you can see here's the crest or the peak. Here's the trough. And it travels via conduction. Conduction in the air, conduction in a solid or liquid. And that's why in water, sound will travel much, much faster than it will through the air, and then through the land even more so. So if you watch an old cowboy film with you got the Native Americans and you got the cowboys, and the Native American tracker in his racist stereotype will then put his ear to the ground and there's this many horses in that direction or whatever. They couldn't. That's obviously a racist stereotype, but that is something you can do. You can hear sound traveling through a solid, stone in particular, much, much better than you can through the air. We can detect these vibrations with our ears. That makes sense. We know that the ears are full. But it is the cochlea in the inner ear which detects the sound. There are a bunch of hairs there that when they vibrate, it sends a little nerve signal to the brain and says it's this frequency here and so forth. And they look like this. So here's our speaker up, and it's like, here's a bit of rarefaction, and here's compression. Here's a bit of this drawing is not perfect, but and there's your wavelength. So from peak to peak or crest to crest. And there are some properties of sound waves. So we can draw it like a transverse wave, and that's actually the easiest way to do it, because then we can look at our amplitude, right? So if the amplitude goes up, so here's quieter, here's louder, the volume also goes up. This is where the term amplified comes from. So amplitude, which is the distance that it travels, distance that the particles travel, not the higher the amplitude is, the louder it's going to be. And if the amplitude goes down, like here in the quiet, so it's a smaller amplitude, the volume goes down. If the wavelength, like this one, goes higher, so here's a long wavelength. In fact, the wavelength would be about here. The frequency, so how often the waves travel past a certain point, a full wave travels past a certain point every second, goes down. And we measure frequency as in pitch. So, high, low, that sort of stuff. So this one here would be lower, and this one here would be higher. Low, low, high, that sort of stuff. And the reason is, the reason is that the wavelength is further apart, so you get less of them per second, because they're still traveling at the same speed, so you get less of them per second, and yeah, that's why. That's your wavelength. So deep pitch, high pitch, so long wavelength, low pitch, small wavelength, high pitch or high frequency. All right, I hope that made sense. If you have any questions, put them in the comments below. We'll get back to them as quick as we can. Thanks for watching. Speak to you next time. Bye now.